2, 1. If it was ready, I would have revealed it. It's not ready. Not that it's a big thing, I just want it to be complete, that's all. All right, I can't think of anything we're going to write down today. Well, I am. You might be interested to write stuff down. Today is our introduction to shapes and geometry. So I apologize in advance if these things are familiar and easy, because you've gotten used to a standard of complexity, and geometry might not live up to that standard. But we'll try and throw some stuff in later on. Definitely not an introduction. But depending on how well you remember your shapes, there might be some things that is new. So we'll see. So don't read all the words. I'm just looking at the table. I'm going to jump back and forth between these guys. When we talk about shapes, we're mainly interested in polygons, coming from the word poly, meaning many, gon meaning angle, so many angle shapes. And my goal is to be able to identify different kinds of polygons and be able to draw some of them, the basic ones at least. Now, unfortunately, because these things sort of got discovered slowly over time, the names have some variety in them as well. Some names end in gon, some names end in angle, some names end in lateral, meaning sides. But if I have a number of sides or angles that go, let's say, above 12, then we sort of standardize the name and just call it an n-gon, where n could be whatever, 14, 15, whatever. The number gets too big, we don't really care about a special name anymore. A 20-sided perhaps could just be a 20-gon. That's 12. Above 12, in general, we don't care to name every single one, only the special ones. But below 12, yes, we want to be comfortable with their names. But first, let's just make sure what is a polygon and what is not a polygon. A polygon has to be a closed shape made of straight line segments. So the first one is not a polygon, it's not closed. B is not a polygon. Not all the line segments are straight line segments. And I also can't cross line segments. So C is not a polygon either. Those two middle ones cross each other. For the same reason, D isn't either. Only two line segments meet each other at a time. I can't have multiple ones crossing and meeting and all kinds of weird things. Only two line segments meet at a time, and nice and closed straight lines. And E is not a polygon either, because those middle ones in the square cross each other.
It's not 5 polygons?
None of them are polygons, no. But for different reasons. So closed shape with straight lines, two sides meet only two, not more than two. So I have an example here. Let's see if we can zoom this in a little bit more. There we go. Identify the following shapes as polygons or not, and do they have a name? So the first one, it's in the book, in case that's a little small. We have 5 sides. That is a polygon, straight line segments, closed, only 2 meet at a point. And that is called a pentagon. Penta meaning 5. So we have names for these smaller ones. Some you may know, some you may not. Even though the first one is a pentagon, the second one is a triangle. But you'll notice that for a polygon, the number of sides and the number of angles are the same, which is why sometimes we refer to the angles, sometimes we refer to the sides, but that number is always going to be the same. It's just sort of tradition from way back. Number 3, is that a polygon?
Yes.
We're a little bit conditioned to think it has to be a nice roundish shape. I mean, that's not a requirement. That's just the ones we tend to draw. That is a polygon. How many sides does it have?
Hexagon?
No, how many first? 7? 7 heptagon. 7 doesn't come up a lot, so you might not be super familiar with that word. Heptagon. Number 4, similar to the previous slide, not a polygon. Even if I see that middle as another meeting point over there, more than two lines meet there, so that can't work either. Not a polygon in number 4. So instead of me writing all this down, I'll just speak slowly and you can write whatever you want. Feel free to stop me if I go too fast. Number 5, polygon, yay or nay? Yay. It is a quadrilateral. Why? It's just how history decided. Quadrilateral. 4 sides. Not a quadrigon or whatever else you might think. It has a name. You can't use another name. The only exception is in the case of 9, it has 2 names. You can call it a nonagon or an enneagon. Who knows why? I don't speak Greek. And the last one's a little hard to see, perhaps. It's not the best resolution pictures I have here. Number 6, is that a polygon?
Yes.
Yes, it is. Yes, it is. How many sides does it have?
10.
10. So it's called a
Decagon.
decagon. So look at the table. Hopefully most of them are familiar to you, but perhaps not all of them. But we'll get to 11 and 12 some other time. It's not crucial right now. I don't want to overwhelm you with the naming system behind these. But they're definitely, like many languages, they have their own exceptions. Quadrilateral, triangle. They don't really fit because maybe they were one of the first ones to be discovered and investigated. And then the other ones sort of got a little bit more standardized in their names. Yes?
What's the most sided polygon in existence?
That has a special name?
Yeah. Like, is there one that you would know of?
No, I don't really know any fancy names.
Dr.
On, there's no limit to how many sides you can have, right?
Do you think someone
Which is why there are so many after a while, we just sort of standardize it to n-gon. And then there could be other words in front of it to indicate the kind of shape, because I can have many different pentagons, for example. So instead of making a name specifically for it, other names, other words go in front to clarify what kind of 100-gon it is. Yeah. But there are so many, yeah, so many. And my goal is to not overwhelm you right now. So, the basic concept of a polygon. There are many, right? Many. And when we get to triangles and quadrilaterals, you'll see what I mean, adding words to clarify which one we are talking about. But if I just say triangle, there are many. Many quadrilaterals, many pentagons, hexagons, though we tend to not draw these kinds of hexagons. We tend to draw the nice balanced ones, but it doesn't make the others any less valid. And of course, the more sides I allow, the more variety that is possible. So we have 2 kinds. An equiangular polygon is one that has the same equal angles. Equiangular, equal angles. Equilateral, equal sides. equilateral. And then if we have both of those requirements, we call it a regular polygon. Regular. So that's what I mean. We put words in front to classify it further. All right. Regular, equiangular, equilateral. Yes?
Is that square?
We're going to get to it. But yes. I think I have an exercise question here. Here at the top, 9.2. Or did I say something there about squares? Yeah, so the remark there at the top, some polygons have special names, even though they don't need to. For example, a regular quadrilateral, I guess because it's so common, has a name, square. Maybe that's what it is. But in general, they don't necessarily have special names. Their name might be regular quadrilateral. 9.2 there. Is it possible to have a polygon that is equilateral but not equiangular? That's a mouthful.
No.
Can we, if you say yes, we're going to have to come up with an example. Can you, I'll give you a second. Can you draw something that is equilateral, meaning all the sides have to have the same length, but it's not equiangular, meaning not all the angles are the same?
Yes, changes everything.
It does.
No.
Some say yes, some say no.
Wait.
If you say yes, you have to be able to make an example. Who wants to come up and share their example on the board? Take your time, think about it. I don't have much happening today. We have 30 minutes to fill. I have no quizzes to give back. We need to stretch this out. This is joking.
I can't guarantee that it's equilateral
Well,
or equiangular, but I'll try.
it doesn't have to be perfect in your drawing, right? Yeah, we already have examples. A star, for example. For the video, I'm going to have to duplicate it here. A star, for example. Well, don't judge his perfect.
They're not
Doesn't
straight
have to
line
be
segments.
perfect.
Yeah, your star drawing skills are.
It was better than mine.
He pre-read yesterday and he knew there was going to be an example, so he practiced drawing.
Yeah,
It was our study group class.
that one was loaded up for sure. Let's pretend the star all has the same length sides, which is very. Ooh.
Chris, who showed him?
Just squint. I need it for the video, all right? Let's take that away. Get rid of that. Get rid of it. But a star and many others. They don't have, when we talk about angles, we talk about the interior angles, and clearly those are not the same, even though the sides can all be the same. But as soon as I require both, then this kind of shape isn't possible. Just to limit my view as an introduction, we want to have as much structure as possible. Yes?
Is it only possible to have the equal sides, different angles by having an
Sort of
inward
indented?
angle?
Yeah, pretty much.
So
Because I'm stuck with equal length sides, I can only sort of flip the outside to inside. I can't do much else. Yeah. Otherwise, they're not going to be equal. Sorry.
Sorry, I interrupted there. When you're counting the angles, it's just the inner angle.
It's the interior angles, yes. So we can think of it as, I'm not saying there can't be one exception, but I can't think of one right now. Because the equilateral aspect really restricts me. I can sort of just indent it. And in that way I can bypass the angle requirement. Yeah, that's pretty much it. All right, so now we have different size polygons. The first one, of course, being triangles. So let's just focus on triangles a little bit more. And I have a fair number of different triangles that you all have to be able to know what their names are and be able to draw one close to accurate. It's never going to be perfect, right? Even if I have a ruler, there's still gaps between the lines. It's never going to be perfect, but as close as I can get. So I have an acute triangle, refers to the angles, and there's an angle, or there are angles less than 90 degrees. Acute, pointy, sharp. A right angle triangle is one with 90 degrees as one angle. Can I have two angles 90 degrees?
No.
I only have three sides, so it's going to be tough. It's going to be tough. But these are the things I need to think about, right? If I have one side, why is that so final zoom in? If I have one side, now I need to have my other side 90 degrees. If I want another 90-degree angle, I can't close the shape. I can't close it. I only have a triangle, so it's not possible. Only one angle can be 90 degrees. I can have one angle nice and wide, bigger than 90 degrees, then it's called an obtuse triangle. Obtuse. But many of these words I think should be familiar to you. And certainly going into elementary school needs to be very familiar. A triangle with all sides different lengths, scalene triangle. And two sides having the same length is called an isosceles triangle. And a lot of elementary school is identifying shapes and properties of shapes and just getting that thinking started. Exercise there, 9.3. Why can I say an equilateral triangle is also an isosceles triangle? And is the reverse true? Is an isosceles triangle necessarily equilateral? That's just one question at a time. Why is an equilateral triangle necessarily an isosceles triangle as well? Now I have to know, what do these words mean? To even make sense of the question, I need to know what the words mean, of course. Why is an equilateral triangle necessarily also an isosceles triangle? Yes. An isosceles requires that I have two sides the same length. Could be more. And if I happen to have the third one also the same, then it's an equilateral triangle. But if I have an equilateral triangle, all three sides have to be the same, so two of them are automatically the same.
So
it's not two and not a third. It's at least two for isosceles. So for example, I need my glove. For example, do you have space here? Sure. I can have, now my drawing won't be perfect. We indicate equal sides like that because our drawings aren't perfect. That's an isosceles triangle. The third one's not the same, right? Just visually it's not. But if I have a similar situation where I get those two the same, and the third one happens to be the same as well, they're both isosceles. Because isosceles requires two sides to be the same. Not exclusively. Just two of them need to be the same. Could be more. Could be more. So I need to understand what these words mean for no reason other than I can't tell little Timmy the wrong thing. I want to teach him from the start because his first introduction is probably going to stick. So if I don't understand these words, then he's not going to understand the words, which is going to create confusion, which is going to create negativity, and so on and so on. So triangles have a good number of special cases. Any questions on triangles?
So just to make sure I'm clear here, does that mean an isosceles can be an equilateral, but an equilateral can't be an isosceles? Is that how it works?
Let's address your first one. An isosceles triangle can be an equilateral triangle. Not always.
But it can be.
It can be, it's possible.
But an equilateral.
An equilateral triangle has all sides the same.
So it can't be.
So automatically two sides are equal. So it's always isosceles as well.
Okay.
So one is sort of contained in the other in one way. Yeah. But not both ways.
Okay.
Because the isosceles triangle is more relaxed of a requirement. The third one can be any length.
Okay.
No questions. It's not like there was only time for one question. Sorry, you don't get it.
Can they be multiple? Because I think about a right angled triangle. You have your 90 degrees in the corner and then connect it here.
Absolutely.
Also be like an isosceles.
A right. Okay, so first of all, a right angle triangle is not going to be an acute triangle, because an acute triangle, each angle has to be less than 90. So the angle ones are non-overlapping.
But could a right angle also be an isosceles?
A right angle triangle can definitely be an isosceles triangle. It's not that boring. I could have, okay, I don't think my sketch is perfect, but I do that and now it's perfect. Certainly possible. Certainly possible. All right. I just want to check what's next on my slides here. There's some stuff about angles, acute, obtuse. Yeah, that's fine. Classifying triangles we did. These things are a little overlapping. Quadrilaterals are next. And I have a bunch. The most structure, the regular quadrilateral, where everything is equal. All the sides are equal. All the angles are equal. That is called the square, which everyone is very familiar with. Then I start to relax some of the requirements slowly. Let's relax the angle requirement, but keep all the sides the same. Then I get a rhombus. Then we can relax, go back to square, keep the angles the same, but relax the sides equal requirement. And we get a rectangle, where the sides aren't the same length, all of them, but the angles are still all the same. They're still all square angles, 90-degree angles. Now I get other properties in the rectangle due to my still pretty strict requirement that the opposite sides do have the same length. That's cool. Then I relax the rectangle requirement a little bit further, that the angles don't have to be the same, and I get a parallelogram if I just have to add another requirement that opposite sides are parallel. So it's not a full relaxation of the rectangle. It still has some structure. All the opposing sides have to be parallel and the same length. So I can sort of a little bit deform the rectangle a little bit. And I won't have all the same angle, but still a lot of structure. Any questions on those four first? Are they all familiar? Can you explain what each one is? Can you draw what each one is? And how they're related to each other? That's our goal here. Just focus on the words that you may not be super comfortable with. Hopefully not all of them. Let's see here. Still have 20 minutes, lots of time. Any questions on these four? You don't have to ask a question. Though I appreciate the effort.
What was the rhombus one again?
Rhombus, all sides are equal.
Most of the times we rhombus and square.
The square, all sides are equal, and all angles are equal. So a square is a rhombus. But a rhombus isn't necessarily a square.
So rhombus, all sides equal?
It's going to be in the book. It's going to be there. I just don't want to show too much. I want to think of the shapes first. We're gonna come back to these for sure. So a little bit different. We have a kite. A kite requires that I have two pairs of adjacent connected sides. and they have to be equal. Think of the first and the last one. See, the top pair of sides are connected and they're the same length. The bottom pair of sides are connected and they have the same length. So, a square is a special kite. But a kite is certainly not a square, necessarily. A rhombus is a special kite, but not the other way around. Because a rhombus, all sides are the same anyway. So if I take two pairs of sides, they are equal already. Some stuff to think about, yeah. But all elementary level stuff, not requiring more at this stage. We might, in some cases, we might dip our toes in something a little fancy, but not a lot. Trapezoids, a little bit more relaxed, where I require that there are two opposite sides that are parallel. That's it. They don't have to be the same length. The other two sides can do whatever they want to do. One pair of opposite sides parallel. And with that slightly less restrictive requirement, I do get more variety. So, square, a rectangle, rhombus, parallelogram, they are all special trapezoids. All special trapezoids. And then, of course, I get others that have no special names, that don't have enough structure for me to really work with. Alrighty. It's over here listed. These are not the only way to define them. There are multiple ways. But if you're not sure, you can use those. This is sort of how I think about them. But there's certainly no one definition for everyone. But I do need to be able to know when is one a special case of the other. Can I draw it? Can I see how these fit into each other? Now, just like we tend to organize and arrange groups of things and making sort of a tree system like that, I can do the same for polygons. So I have my family called polygons, and then the first split is according to, get rid of that, sorry, there we go. The first split is according to how many sides. And then within the triangles, I have different kinds of triangles. And we said that I can go, a special isosceles triangle is an equilateral triangle. So they are sort of below each other. And in the quadrilateral section, there are more connections, one being a special case of the other, and so on. So it's important to understand why those connecting lines are there and check your understanding of which one is a special case of which one. Like we said, the rhombus can be a special kite, but kites are higher because it contains more things, not just the rhombus. So when a certain type is contained in something else, then it's below, connected with a line. And then past that, we just have regular or not regular. We don't really worry about it any further for our level. Any questions looking at that tree, which is also in the book somewhere? It's on page 66. Any thoughts or questions on that so far? Do you know most of those names already? Maybe just a little brush up, fine-tuning of what they mean exactly. Now, the whole thing with geometry that we sort of just get a small little glimpse of. The main issue is I can't always just trust how things look and make conclusions on that. There has to be a specific rigid system for examining shapes and referring to shapes and measuring and so on. If I look at the first case there, the line that looks to be perpendicular to the bottom PQ line, they don't look to be the same length visually to me. But I can't always trust my senses to make accurate sound conclusions when they actually are the same length. The middle ones, the presence of those arrows really messed me up. And those lines do not look equal length, the straight lines, at all. The PQ one, with the arrows pointing outward, look longer than the other one. But they're exactly the same length. So my perception can very easily be incorrect. And geometry as a science is aimed at describing things in an objective, unbiased way. Especially when I try and represent three-dimensional objects on a two-dimensional surface, I get the last shape, which is called the impossible triangle. If I look at that long enough and track the sides, the outside at the top becomes the inside, becomes the outside, becomes the inside. That doesn't make any sense. So if I do a two-dimensional drawing, I can make things look realistic that can't necessarily happen. It can be a trick. Yet, how do we feel about this impossible triangle? Do you see the problem? Something's not right with this triangle in terms of the sides. Do you see it? This side, for example, is sort of an outside side, right? It's on the outside. Then if I track it, it becomes a side, sort of alongside this bar at the top. And then it becomes the back side, which then changes to this inside. Something doesn't feel right. Doesn't feel right. Yet, somewhere in Australia, I don't know where, they built it. They built the impossible triangle. I can't remember where it is, unfortunately. You can Google it. See how it looks weird, right? The outside is the inside is the outside, especially the shading. You can keep track of them. Something's not right. And if I look at it and track where the sides go, sometimes something doesn't seem possible. But it's right there. How did they do it?
It's not around the same concept of a Mobius strip, is it?
In a way, yeah. In a way. Not quite the same. The answer is they cheated. It's not a triangle. There's a gap. And if you walk around it and go to the correct spot, that little indentation there makes it seem as if it fits perfectly. It doesn't actually fit. It's impossible.
No, it's just disappointing.
But if you stand at the right spot, then it looks perfect, yet impossible. So there's a lot of things that look possible, yet they are not. Let me just zoom out. There's another one there. I need to zoom. This is sort of the start of that concept, the impossible staircase. Yes. You go up and you never stop going up. Which is something that MC Escher exploited a lot. Let me just go full screen here, perhaps. Making something a little more interesting with the impossible staircase. They're just going to keep climbing forever. Up or down? Hopefully down. I can't remember the name of this one. Something with water, obviously. That the water falls down and up. Yeah. It's because I'm trying to, well, not me. The idea is representing a three-dimensional concept on a two-dimensional surface. You can cheat, and the perception looks right, yet it's impossible. Here, I'm going to zoom out. If you look at those lines, they are not parallel. No one can look at that and say it's parallel. Obviously not, right? Yet if I remove those little angled lines, they are the same lines. They're perfectly parallel. My perception is completely changed with the presence of these other little lines. And I can't trust my perception at all. I need measurements, something accurate. Same with that. Those lines do not seem parallel. But they are. They built this. And it looks to be a horrible, horrible construction there. But it's the presence of the lines and the squares. And it's actually, everything is perfectly level, perfectly designed. But it looks horrible. It looks as if someone measured completely wrong. But if you measure it, it's all perfectly level and parallel. Can I go back here? Oh, well, that was the end? There was one more. Things like this, the presence of those lines make one person look bigger than the other. The left one looks bigger, but they're the same person.
I mean, you keep changing the picture and saying this, we're just assuming you're telling the truth at this point.
No, I am telling the truth.
You didn't take a measuring tape.
No, you would have to, and then you can confirm it. If you have a long enough one, reach, you can measure them. The presence of the wall and the way the path goes makes one bull look bigger than the other one. But they're exactly the same. I can't trust my perception. I need accurate measurements and ways to conclude things without me just looking at them. That's the point of geometry.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.